Okay, so just showing you these at the top again. Okay, these are the big ideas. Have your kind of be on the lookout for these as we go. See if you can pick them out. Okay, so what are the plate tectonics? What's that big idea? That's kind of a big idea, but what are they in general? Okay, what's a convection current? What role does it play in plate tectonics? What is a converging boundary? What is a diverging boundary? What is a transform boundary? You can tell we're going to learn about 3 types of boundaries today. Okay, which of the 3 types are likely to have volcanic activity, and which of those 3 types are likely to have seismic activity? Again, seismic means earthquake, so be on the lookout for earthquakes today. Okay, so last time we really went through Alfred Wegener's theory of continental drift, all the evidence for it, right? Hopefully I left you convinced that yes, the continents are moving, right? They kind of have to be. There's just too much evidence for them not to be. And if you don't buy the indirect evidence, well, we see it happening with our satellites, right? We can actually watch them moving slowly every year. So they are moving. How does it happen though, right? So if you accept that they're moving, your next question should be, well, how are they moving? Okay, good question. Let's find out. So it's through a process called plate tectonics. Okay, what are these plates that we're talking about? Well, essentially, the lithosphere, okay, is broken up into 7 giant pieces. Hey, how many continents are there? Do you remember that from your elementary school geography? Right, there's about 7 continents. So there's 7 big plates. Okay, there's some smaller ones too as well, but essentially there's these 7 huge plates that the lithosphere is broken up into. So it's literally cracks in the lithosphere, right? It's broken up into these plates, right? And do you remember when we were talking earlier, we said, hey, the lithosphere floats on top of the asthenosphere, and the asthenosphere kind of flows, even though it's solid, it flows like silly putty over long enough times. And we kind of said that was going to be interesting later. Well, here's where it gets interesting now, right? Imagine if you're a boat, right? Because that's essentially what the lithosphere is now. If you're a boat floating on top of an ocean, right? And that ocean is moving, it has currents and it's flowing over time, what's going to happen to you in your boat? Well, you're going to get moved, right? You're going to get moved around by those currents. So that's exactly what ends up happening, okay? This is why the plates are spreading. Remember, we said Africa and South America were spreading away from each other, okay? What's here again? Pop quiz. What's this stuff, right? That is our mid-Atlantic ridge, okay? They are spreading away. New rock is forming and pushing one another away. So we call these plates tectonic plates. Tectonic plates. Why do we call them plates? Well, they're big flat pieces of the lithosphere. I mean, they're curved with the curvature of the Earth, obviously, but they're essentially just these big plates that are floating on top of the asthenosphere, okay? So plate movement occurs because of convection currents in the asthenosphere underneath the plate. So what is a convection current? Good question. Okay, first I'll let Bill Nye talk about it a little bit. Okay, just the general idea. Then we'll come back and we'll look in more depth at what a convection current is. Okay, because you see it happening in the video, but it doesn't necessarily explain how it happens, why there's a convection current, which we do kind of need to know.
Hello. Today on Consider the Following, I'd like you to, well, consider the following. You and I are sitting on the Earth's crust, and it seems pretty solid, doesn't it? But now scientists believe that the Earth's crust is actually made of plates. Not cheap plastic picnic plates like this, but tectonic plates. And tectonic is from the Latin word for build. So the Earth's crust is built of plates. Plate tectonics. And the plates are floating on the Earth's mantle, which you know is molten metal. It's kind of like corn syrup. In fact, scientists actually use corn syrup like this to do studies of what's underneath the Earth's crust. Scientists first caught on to the idea of tectonic plates when they realized how well South America seems to fit in next to Africa. Not that bad. So take a look here. Here we have the camp stove of science. And in it we have models of tectonic plates. See, right now they're all together. And scientists believe that at one time, all the plates of the Earth's crust were one piece called Pangea. And Pangea, well, that means whole Earth, see? Not that bad. Let's say this is the Earth's crust. You see, where the plates, the tectonic plates, are spreading apart, that's where we get volcanoes. And where the plates are coming together, that's where we get mountains. Now, you know, the plates are still moving even today. In fact, North America is moving away from Europe about this much every year, about 2 centimeters, about an inch every year. Well, thanks for joining us on Consider the Following.
All right, so I do want you, please do draw this out, or at least make sure you know how you could draw it out on your own. So essentially, here's how it happens, okay? Here's 2 plates. We'll have, okay, it's a piece of the lithosphere, so we'll say lithosphere, and let's just call it plate 1. Maybe it's the one with South America, okay? Over here, we have another plate, remember, because the lithosphere is actually, it's kind of cracked up into different plates, right? Over here, we have another plate. It's also the lithosphere, okay, but maybe it's plate 2. Maybe this one is Africa. Now, what's right below the lithosphere? Remember, Lisa always mixes Oreo cookies and ice cream, so Lisa always, that's lithosphere. Right below that should be our asthenosphere, right? So this is our asthenosphere. Okay, now what was interesting about the asthenosphere? Do you remember? Remember, the asthenosphere was solid, right? All layers are solid except for the outer core. That's a liquid, but all layers are solid. But remember, the asthenosphere was solid, but over long enough times, it would actually flow, right? Kind of like silly putty or Play-Doh. Those are both solids, but if you leave them out long enough, right? If you ever let silly putty out, it eventually kind of flattens into a puddle, right? And so over very, very long times, you can start to get flowing in the asthenosphere. Now, I'm going to draw something else first. Okay, what's below the asthenosphere? Lisa always mixes. So below that, you have and the mesosphere is actually way bigger than this, but the mesosphere is not super interesting. I just kind of need to draw it, okay, just so we have it there. What's below the mesosphere? Lisa always mixes Oreo cookies and ice cream. Okay, so below all of that, we have our inner core and outer core, right? Can I just call it the core? Is that okay? Now, what does the core win at in terms of layers? Well, pretty much everything, right? It's the densest, it's the most pressure, but hey, it's also the hottest, okay? It's the hottest. So the core is providing a lot of heat, okay? A lot of heat. So essentially the core heats up, right? It heats up this. Now, if you're the asthenosphere and you're kind of sitting on top of this hot core, like you see here, right? Well, where are you the hottest? Are you hotter up here or are you hotter down here? Well, yeah, you're going to be hotter right down where the heat's coming to hit you, right? It's like putting something on a pan. The part that's actually touching the pan gets hot first, okay? And so what ends up happening is that you have hot magma, okay? Hot magma is going to end up rising. Remember, magma, just melted rock, right? Magma is melted rock. So here we go, it rises, okay? Here we have our mid-ocean ridge, okay? So hot magma rises. Now, as it gets up here, what's it going to start to do? Well, first of all, it's getting further away from the heat, right? So it's going to start to cool, okay? You've heard that hot stuff rises, right? Why does hot stuff rise? Remember, as something gets hotter, its particles start moving faster and faster, which means they get more spread out, which means, hey, it's less dense. Remember, less dense things float, okay? Normally, I would point out to you in my class, look around. The heater is all along the floor. That's because when the hot air comes out, it will rise and then kind of mix evenly throughout the room. Whereas the air conditioning is on the roof because cold air is denser. So you want it to come out and fall down and spread through the room, okay? Unfortunately, you can't see that in my room right now, but maybe you look around your house, you'll find the same thing. Where are all your floor heaters? They're probably, well, I just gave it away. They're probably on the floor, right? Or at least on the lower parts of the wall. There's probably not too many heaters above you because you want that heat to rise and mix evenly throughout the room. Okay, so the hot magma rises and then it gets cooler as it gets up to here, right? Partly because it's exposed, but also just because it's getting away from the heat. So the cool starts to fall, right? Cool magma falls. Okay, same thing kind of happens here, right? It's getting heated up, it's getting cool, and then it's falling. Okay, hot rises, cold falls. By the way, how do we get the mid-Atlantic ridge starting to form? Well, some of that magma is going to actually bubble out, right? You can see some of that is actually going to bubble out and start to cool, okay? And look what it's starting to build, right? It's starting to build kind of a mountain there. So some cooled magma essentially sticks to the plate, giving new lithosphere, right? That is now a part of the lithosphere. Congratulations. It just graduated from the asthenosphere to being part of the lithosphere. Not only that, but notice how it's not going to heal itself perfectly, right? It's kind of going to bubble up and then more is going to bubble up, and you're kind of going to be building a mountain range almost, right? Hey, what did we say a mid-Atlantic ridge was? It's basically a mountain range. So this gets built up. We have our mid-ocean ridge forming, right? That's what's happening there. So have you ever had like a really bad scar, right? And when it healed, does it heal perfectly flat? Not quite, right? I've got a couple bad ones, and I know they kind of get bumpy, right? That's because the similar kind of thing is happening here. The earth basically has a big crack in it, a big cut, if you will, right? And so it's kind of getting patched up over time. I mean, that's not quite what's happening. It's not getting plugged, but it's just not perfectly kind of getting filled in smoothly, right? As that magma is coming up and bubbling over and cooling out, it's kind of going to build up and up and up and up into a underwater mountain range known as a mid-ocean ridge, right? Okay, and so I want you to look at these two things we've drawn here. Okay, first of all, these are called convection cells. This process of cooling and of heating and rising and falling and cooling, that's actually known as convection. That's one of the ways heat is transferred through a fluid, right? Is just by hot stuff going up, cold stuff going down until it's all swirled around. So this is the process of convection, okay? These are convection currents. So I'll highlight in purple so you know it matches. Okay, those are convection currents. So I want you to look at both of those and imagine them in your mind. Imagine this one, actually physically take it and turn it this way, okay? So turn it the way that it's actually turning. It goes this way and this way and this way and this way. Hey, what's this lithosphere gonna do? If this wheel that it's on is turning this way, right, what's it going to start to do? Well, it's going to move, right? It's going to move that way. So plate moves this way. Now do that with this one. This one's rotating this way and this way and this way. What's it kind of pushing this guy to do? Well, it's going to make it move that way. Essentially what you have here is like a conveyor belt, right? You have something on top of some wheel that's pushing it that way, rolling that way constantly, sliding them away that way. That is why scientists believe the continents move, right? Is because of these convection currents in the asthenosphere. Okay. Now, plate boundaries are just places where two plates meet, two tectonic plates. So you've already seen a plate boundary, right? This is one. These are two plates and they're meeting, okay? We'll learn in a sec what you would call this type of plate boundary, right? But you might already be thinking to yourself, I bet the plate boundary is a gnarly place to be, right? That's basically a crack in the lithosphere, a crack in the surface of the earth. Right below us is the asthenosphere and magma, right? And you'd be right. There's a lot going on in a plate boundary. The earth is literally moving there. I mean, it's moving everywhere, but it's really, really happening. That's the source, right? So wherever two plates meet, they're geologically active, we say. What does that mean? Essentially, it means lots of earthquakes, lots of volcanoes, okay? That's what geologically active means, which kind of makes sense. You've got some pretty wild stuff happening here, right? You've got the tectonic plates that make up the entire surface of the earth. When you put them together, you've got them either spreading away, moving towards, or rubbing against each other. That's going to be pretty wild for the people living near or on that. So the first of the three types is the one that you've already seen, a diverging boundary, okay? So when roads diverge, you might have heard of a diverging path or a diverging trail, okay? Means they spread. They go in opposite directions, okay? So the plates move away from each other. Now, as we saw in the last one, what was happening? Was new lithosphere being formed or destroyed? Let's go back. Let's look at it, right? Well, look at it. New magma's bubbling out, cooling and hardening, right? That's now become part of the lithosphere. So new lithosphere is formed, okay? Usually into a ridge because it's not going to be nice and clean. Like we said, it's going to be kind of like a scar where it gets a little bumpy, right? So the lithosphere, okay, this is a diverging boundary. The two plates move away from each other. Now, there are high levels of volcanic activity. You can probably guess why, right? This is literally the asthenosphere. That's a whole bunch of magma, right? It's kind of just one big volcano along the mid-Atlantic ridge, right? There's a whole bunch of magma constantly kind of coming up. So a lot of volcanic activity. Just as a note, there's also seismic activity, which is just earthquakes. Okay, I'll tell you right now, wherever you have two plates meeting, you are going to have seismic activity. All three of them. Those are earthquakes. The next type we have is a converging boundary. So diverging and converging are opposites. Okay, so converging boundaries are where two plates collide and come together. Okay, so two plates are colliding here. They converge. Okay, so you can see that here in the picture. Right now they're coming towards each other. Now, what's slightly different here is that one will be slightly more dense. And as we know, when things are more dense, they sink. Okay, so it will kind of dip under a word that we call subduct the other. Okay, so again, converging boundary means essentially they are colliding, they're coming together. Now, when this happens, okay, notice how here we have two colliding, right? Two coming towards each other. Look at this guy. This guy must have been less dense. So it is dipping down underneath the other one. Hey, as we go down, what happens again? How does the Earth change as we go down? You're right, it gets more dense and it gets more pressure, but here's the big one. It gets hotter, right? Eventually, it actually gets hot enough to melt this lithosphere, okay? So if it gets hot enough to melt the lithosphere, we're doing the opposite of what we were doing at the diverging boundary now, right? Now, old lithosphere is destroyed. So it gets subduct and then melts, right? It gets low enough down that it's actually going to get hot enough to melt. Okay, gonna melt. Now, have you ever tripped on a carpet or a rug, right? Where you kind of slide into it? What do you notice happens to the rug? It kind of starts to get scrunched up along the way, right? That's kind of how you get mountains, okay? And if this is happening, if it's getting deep enough down, it's actually going to melt, and that's going to make a whole bunch of volcanoes, okay? So volcanoes are fairly common at converging boundaries, especially where an ocean plate is meeting a continental plate. So in other words, where a plate from the ocean is meeting a plate from the land, okay? So for examples of that, you could see the Cascades in BC, Mount St. Helens down in Washington, okay, along the west coast there. That's a volcano. I think it last went off at least a big eruption back in the 80s, okay? But those are formed by the Pacific plate colliding with the west coast of our North American plate, okay? So mountains always form nearby. Sometimes volcanoes form nearby. You can definitely have volcanoes at a converging boundary. I'll show you a quick video to kind of help you visualize how do mountains come out of this, right? But it kind of comes down to a crumpling motion.
How do mountains form? We see them in just a moment of time, but they form over millions of years. Mountain belts extend for hundreds, even thousands of kilometers, and their structures penetrate deep into the earth, so their size and age make their formation difficult to understand. French geologist Jacques Malavier builds sand models that mimic the formation of mountain belts and allow scientists to study this complex process.
Sand is a very good material for simulating rock deformation.
Mountain belts are created when continents collide. In this experiment, we see two continents separated by an ocean. Now watch what happens as the plates converge. As one plate subducts or dives beneath the other, the ocean basin closes. The continental crust, which is lighter than oceanic crust, cannot be subducted. Instead, as the continents collide, the crust thickens and is forced up. Note how the sand is folded and faulted. We see similar structures in the rocks in mountains. One important factor not accounted for in this model is erosion. Erosion exposes the deformed rocks that were once deeply buried in the mountain belt. The green sand represents the rocks of the ocean basin. Note that it's been trapped between the two continents, marking their original boundary. These too we see in mountain belts. It's very difficult to understand the deep structure of a mountain belt by direct observation. The sand model allows us to compress time and space and simulates the internal structure of mountains.
Okay, and finally, the last type of boundary we've probably are thinking, well, we've seen them when they spread, we've seen them when they come together, when they collide. What's left to do? Well, to do neither. So that's to just move kind of past each other, right? So that's kind of the last option, right? Is for them to just kind of shimmy along each other. So two plates slide past each other, okay? Now here, okay, now in the first one, we had that a ridge would be formed, right? A ridge would be formed at this one. That made sense because the magma was kind of bubbling up and forming a mountain range, sort of, right? This one, we had that a trench would be formed, which does make sense when you look at what's happening here, right? One's dipping into the other. If you kind of take your hands and do this subduction, this converging boundary, you'll notice that right where your fingers meet your other hand, you'll see that there's a bit of a dip there, right? So that trench is common in a converging boundary, okay? However, if you take your hands and just kind of rub them against each other like a transform boundary, you'll notice that there's really not any significant land feature forming there. Okay, it doesn't mean this is a boring place to be. It does, however, mean that, so like in our converging boundary, we don't have it go the lithosphere going down to melt and form volcanoes. We also don't just have basically a big volcano driving the whole thing. So it shouldn't be too much of a surprise that you will not have volcanic activity at a transform boundary. Okay, so at a transform boundary, no volcanoes. Okay, and for a similar reason, you don't have lithosphere dipping down to get melted, but you also don't have new lithosphere bubbling up from below and magma hardening. So lithosphere is neither created nor destroyed. Okay, however, you will definitely have seismic activity. You will have earthquakes there, okay? Think about it. You're rubbing two things next to each other. They're essentially, imagine holding two bricks and rubbing them back and forth. You're going to feel vibrations. So will the people that live near this transform boundary. Okay, so one example is the San Andreas Fault down in California. Okay, those are transform boundaries. They're not colliding, they're not spreading apart, but they are just kind of moving past each other. And every now and then they kind of catch and they knock and you get a jolt, an earthquake. Okay, so you have lots of earthquakes in that part of the world. And sorry, one more thing for converging boundaries, those also have earthquakes. Okay, so all three have earthquakes because wherever plates are meeting, you're going to get bumps, right, that form earthquakes. Okay, converging and diverging have volcanoes. Transform do not have volcanoes. And so here's kind of a summary of all three in one picture, right? Here you see the transform rubbing past one another. Divergent, diverging, that means they're spreading away from one another. Convergent, lithosphere destroyed, right? One's subducting underneath the other, they're colliding, okay? Again, here's all three showing their kind of motion there. Okay, this video is great. It's a little kiddie, I know, but it actually does an awesome job of wrapping up pretty much everything we've talked about.
Enjoy this movie, then visit brainpop.com for much more. Dear Tim and Moby, when I look at a map, it seems like some continents fit together perfectly. Are my eyes playing tricks on me? From Georgia. You're not seeing things, Georgia. Some continents look exactly like puzzle pieces that snap together. Early mapmakers suspected that they were once all connected. In the early 20th century, a scientist named Alfred Wegener called this supercontinent Pangaea. He thought different chunks of it broke off and slowly moved apart. Over millions of years, they formed the continents we know today. Wegener couldn't explain why Pangaea split up or how. But there was some evidence to support his idea. Fossils from similar plants and animals had been found oceans apart. The age and type of rock layers matched up too. Wegener's theory of continental drift provided an explanation, but his ideas weren't taken seriously until long after he died. In the 1950s, scientists began mapping the Mid-Atlantic Ridge. It's a mountain range running 10,000 miles along the ocean floor. Tests revealed that the farther you got from the ridge, the older the seafloor was. So a geologist named Harry Hess proposed a revolutionary idea. New seafloor was forming at the ridge and spreading outward to make room for more. In other words, the surface of the planet was moving. Hess called this process seafloor spreading. It seemed to indicate that rock was being forced up from inside the planet. Nowadays, we can see this rock formation in action. Wegener had guessed something like this, but he had no way to prove it at the time. As he suspected, there's a lot going on beneath the Earth's surface. Up here, everything seems pretty cool and stable. But miles below our feet, it's a raging inferno. The deeper you go, the hotter it gets. Earth's center, or core, is as scorching as the surface of the sun. All that energy wants to escape, like steam inside a boiling kettle. It pushes outward, putting immense pressure on the middle section, the mantle. Standing in its way is the lithosphere, a rigid layer of solid rock. Well, the lithosphere isn't like a smooth shell. It's cracked into pieces, each one a different shape, size, and thickness. We call those pieces plates. Yep, the mid-Atlantic ridge is the border between several plates. They're being dragged apart by forces from deep inside the planet. You can think of it like a pot of soup. The Earth's core is the burner, and the mantle is the boiling soup. As the soup near the burner heats up, it becomes less dense and rises. When it gets to the top, it cools off and sinks down toward the heat. In physics, those are called convection currents. A similar process is driving the mantle, and it's taking the plates along for the ride. That movement is called plate tectonics. It's the engine driving the constant transformation of our planet's surface. Plates have been bouncing off each other for eons. The oceans have expanded and contracted. Land masses have smashed into each other and broken apart. The plates move about as fast as your fingernails grow, so we don't see the ground sliding around under our feet, but we do sometimes feel it. Yep, I'm talking about earthquakes. Seismic activity is greatest along plate borders. At convergent boundaries where two plates collide, at divergent boundaries where they pull apart, and at transform boundaries where they slide past each other. At all three boundaries, there's enormous pressure on the Earth's crust. That's the topmost layer of the lithosphere. The pressure can build up for years. The longer it takes to release, the bigger the earthquake. Yep, and plate movement drives volcanic activity, too. At divergent boundaries, like the mid-Atlantic ridge, there's a gap in the lithosphere. So magma, molten rock from the mantle, is constantly pushing up along the boundaries. These are the most volcanically active places on Earth. Volcanoes are also common at boundaries called subduction zones. That's when a dense ocean plate converges with a lighter continental plate. The heavier plate gets pushed below, down into the mantle. Some of it melts, and the magma erupts farther inland. The Ring of Fire is a massive chain of these volcanoes. Dense sedimentary rock making up the Pacific seafloor is subducted, transformed into metamorphic rock through pressure and heat, and then recycled as igneous rock through volcanic eruptions. In other words, plate tectonics drives the rock cycle, the constant process of transformation and renewal of the Earth's crust. It also creates our most prominent geologic features, mountain ranges. That happens when two continental plates converge. Since they're both about the same density, neither one subducts. Instead, it's like a slow-motion car crash. The plates buckle and warp. The land pushes up into jagged peaks. The Himalayas are still growing from a plate collision that began 500 million years ago. Yeah, Alfred Wegener's theory has come a long way in 100 years. He was practically laughed out of the scientific community for his ideas. But today, plate tectonics is the unifying theory that ties together the entire field of geology.
When we come back next time, we'll look at what's some of the stuff that goes on at those boundaries, like, for example, earthquakes. Okay, so that actually wraps up this week's material for offsite learning. Okay, if you're looking for practice with this stuff, check the Google Classroom or the agenda for which questions go with it. Okay, and just bringing these up again at the end for you to take a look at. So pause the video, read them, go through them, right? Answer them in your head or on paper, but just check with yourself. Can you take the big ideas from this topic? Do you feel okay about that? If not, go back to your notes or go back in the video and see if you can find an answer for them. And then if you've done all that, you're feeling good about it, you're feeling comfortable, you will be ready to do the check-in for this week, the Google Form summative. Okay, see you next week. Don't forget to come in to Flex if you need me, right? Any questions at all, or if you just want to talk, okay, I'm always up for it.